Muy bien, buenos días a todos. Tenemos el gusto de tener al doctor Mauricio Bustamante aquí en el coloquio del Departamento de Física del CINVESTAF. Voy a hacer una breve presentación de nuestro expositor de hoy. El doctor Mauricio Bustamante realizó su licenciatura y maestría en física en la Pontífica Universidad Católica del Perú. En el transcurso realizó estancias de investigación en México y España y el laboratorio Fermilab en Estados Unidos. Luego realizó sus estudios de doctorado en física en la Universidad de Würzburg, en Alemania, y en DESY. Realizó estancias postdoctorales en el Center for Cosmology and Astroparticle Physics en Ohio State University, en Estados Unidos, y en el Niels Bohr Institute de la Universidad de Copenhagen, en Dinamarca. En 2020 obtuvo un apoyo de 1.3 millones de euros en financiamiento por el Billund Fonden para formar su propio grupo de investigación en el Niels Bohr Institute de Dinamarca, en donde obtuvo una plaza de profesor. Sus temas de investigación se centran en el estudio del flujo de alta energía de neutrinos astrofísicos descubiertos por IceCube, la conexión entre estos neutrinos y los rayos cósmicos ultraenergéticos, así como la exploración de física más allá del modelo estándar de neutrinos de alta energía. Ha publicado cerca de 30 artículos en estos temas, con casi 1.400 citas según la base de datos InspireHep, además de haber participado en varios reviews, white papers y lecturas. Es referee en revistas de alto prestigio en el área como, revistas como PRL, PRD, JHEP, EPJC, JCAP, Communication Physics de Nature, entre varias otras. Ha ofrecido más de 120 pláticas especializadas en distintos foros. Desde 2019 es miembro de la colaboración IceCube Gen 2 y de GRAN desde 2015. Te agradecemos mucho otra vez, Mauricio. Me podría pasar aquí horas diciendo tu currículum. Realmente es un placer tenerte por acá.
Muchas gracias, Iván. El placer es completamente mío. Y si está bien con todos ustedes, permítanme hacer la charla en inglés porque así no tengo que estar cambiando entre castellano y términos en inglés, sino es todo un solo lenguaje. Okay, I'm going to switch to English now. All right, thanks everybody for being here. And I have a special place in my history, academically and personally, for Mexico, and I'm going to say something about that later on. But first, let me start by the beginning. So, as you heard, my work is in neutrinos, and neutrinos are, you know, elementary particles, which means they're indivisible, they're electrically neutral, so no electric charge. They're very light. They're so light that we don't know what their mass is. And they are superbly antisocial. It means that barely interact with matter. And all of these properties are unique when you put them all together, and they allow us to do things that would otherwise not be possible with other particles. And not only that, but neutrinos are ubiquitous. In energy, they span many orders of magnitude, more than 20, as you see here. And in flux, in the y-axis of this plot, they span also several orders of magnitude. So let me just say a few things about this. On the left-hand side at the lower energies, these are the relic neutrinos left over from the Big Bang. They're abundant, like the cosmic microwave background, but not detected yet. They are very low in energy, so it's very difficult to detect them. Towards the 10 to the 6 to 10 to the 9 EV range, those are the usual suspects. These are the atmospheric neutrinos, the neutrinos from supernovae, the neutrinos from the sun. And these are abundant, and most of them are detected. And most of what we know about neutrinos come from these plus reactor and accelerator neutrinos as well. Towards higher energies, 10 to the 12 EV, so TeV, up to about 10 to the 15 electron volts, those are the high energy neutrinos of astrophysical origin that we have discovered barely a decade ago, TeV to PeV neutrinos. And there is one further holy grail of high energy neutrinos, and those are the PeV to EV neutrinos that have been predicted for decades at this point, but we haven't seen yet. And I'm going to say a few words about how close we may be to finally detecting them. And my talk is going to be about these high energy and ultra high energy neutrinos of cosmic origin. And this is an exciting field, especially in the last few years. So not so long ago, we barely knew anything about them, and we had only predictions. So we had a few predictions about the first high energy cosmic neutrinos, at the beginning of the 2010s and the 2000s. And only a few years ago, IceCube, the largest high-energy neutrino telescope currently in existence, discovered neutrinos of PeV energies. Remember, PeV is 10 to the 15 electron volts. So these are the highest neutrino energies that have been seen so far. Today, we're finding the first astrophysical sources of astrophysical neutrinos, or hints of them, and we're performing with them, with the neutrinos that we have seen, the first tests of neutrino physics at energies that otherwise would be unreachable. But in 10 to 20 years, we of course want to be further down the line in our understanding of particle physics and neutrinos in particular. We hope to have discovered neutrinos of EeV energies, so 1,000 times higher energies than today, 10 to the 18 electron volts. And we hope to test those first new physics, turn this new physics test that we're doing today into precision tests of PeV neutrinos and move them also into the EeV range. Question is, of course, how do we get from today to 10 to 20 years from now? And I'm going to touch upon what we're doing today, planning for the future. Now, what makes these high energy and ultra high energy cosmic neutrinos exciting? And there are two reasons why I believe they're exciting. So in a plot of neutrino energy in the x-axis and travel distance from the sources to the detector in the y-axis, all the usual neutrinos that we have studied over the years are towards the low end in both axes. So reactor neutrinos, solar neutrinos, long baseline, short baseline neutrinos, atmospheric neutrinos, very short baseline neutrinos. Supernova have a bit higher energies, sorry, a bit higher, longer distances, but all of these are towards the bottom left corner of the plot. And the opposite side are the neutrinos that I'm going to talk to you about today. And these are the high energy and ultra high neutrinos. So these are the neutrinos with the highest energies that we have seen so far. And those energies allow us to do two things. The first is to study the sources of non-thermal particle emission in the faraway universe at the highest energies. So the most extreme violent astrophysical phenomena that could give rise to particles of these extreme energies. And the second thing is they allow us access into energy scales to test new physics at otherwise unreachable scales. Also, they travel the longest distances. Essentially, they travel the breadth of the observable universe, like a few gigaparsecs. And that means that we're seeing signals from the edge of the observable universe on the one hand, and on the other hand, when we're looking for small new physics effects by studying high energy neutrinos, each effect may be individually small, but if the neutrinos travel for gigaparsecs from the sources to us, then those effects can accumulate and become observable by the time the neutrino flux reaches Earth, and so we can study them that way. Not only this, two reasons that we have to be interested in high energy cosmic neutrinos, but also there's a lot of experimental effort that is ongoing today and that is going to become a reality in the next few years. Towards the left hand of this plot, you might be familiar with some of the experiments over here: Juno, Dune, Super K with gadolinium, Hyper K. These are all detectors that are currently being built or being planned, and they will study neutrino properties and like that come, for instance, from neutrino oscillations. And we are going to be centered at the highest energies, where there's also a host of experiments that are being either upgraded or will continue running in the following years, or completely new experiments that are being planned today for the next decade or two. And these include IceCube, as I said earlier, the largest neutrino telescopes in existence, and also two slightly smaller ones, KM3net and Baikal GVD in Russia. KM3net is in the Mediterranean Sea. And at even higher energies, there's several different experiments that are being upgraded or designed with completely different technologies, including radio, fluorescence detection from under the ice to on the surface of mountains, to some of them on satellites in space looking at the Earth. And all of them will target the discovery of ultra-high energy neutrinos. So that's what my talk is going to be about the interplay between the theory and the experiment to test neutrino physics at the highest energies. Now, let me take a parenthesis here, because I know the audience is probably pretty diverse. and some of you may come from collider physics. When I say high energy neutrinos, I mean TeV to PeV neutrinos, so 10 to the 12 to 10 to the 15 electron volts. And those are discovered, as I'll say in a few slides. And when I say ultra high energy neutrinos, I mean neutrinos of 100 PeV or higher energies. And those have been predicted, but are still undiscovered. All right. Now, the study of cosmic high energy neutrinos falls under the umbrella of astroparticle physics. And there are two sides to the coin of astroparticle physics. On the one side, we observe particles and we try to find from them properties about the sources that where they were born. And by particles, I mean not only neutrinos, but also cosmic rays, gamma rays, and also gravitational waves. And for instance, we can study violent phenomena like a blazar, like the one you see here. This is an active galactic nucleus, so a galaxy with a supermassive black hole that is currently active and spewing out matter in jets. When the jets are aligned towards the Earth, we might see signals, including neutrinos, at the highest energy. So we learned things about distant sources of high energy non-thermal emission. And on the opposite side of the coin, we use the same observations, but now we learn about particle physics. And this is where there's a host of things that we're learning that we couldn't have learned otherwise. For instance, we can measure neutrino cross-sections at energies much higher than accelerator neutrino energies, or we can study neutrino-neutrino interactions, or neutrino scattering on the dark matter in the Milky Way, or the decay of neutrinos along the way from their sources to us, the decay of dark matter into neutrinos, new interactions between neutrinos and electrons, the violation of fundamental symmetries like Lorentz invariance, or the existence of not only the neutrinos that we know, the active ones, but also sterile neutrinos. So there's very many different models that we can study with these high energy neutrinos that we could either not do with lower energy neutrinos, or that we can move into a new regime of energies by using these new neutrino energies. Now, talking a bit more in detail, let me just tell you what makes the study of high energy neutrinos for fundamental physics so interesting. And the fact of the matter is that there's numerous neutrino physics effects that grow as you see here. So some power of the neutrino energy, the power is n, times the propagated distance of the neutrinos from the sources to the detectors, and some coupling that is native to the model that we're trying to study. So that means that the longest the neutrino travels, the more intense the effects, the higher the energy of the neutrino, the more intense the effect. And for instance, just as for examples, the energy dependence is like 1/e for neutrino decay, is energy independent for one type of Lorentz violating terms, and is proportional to the energy for a different type of Lorentz violating terms. If we have neutrinos of PeV energies that travel from the sources to us over a distance of a gigaparsec, then that means that we can be sensitive to coupling sizes that are extremely tiny, like 4 times 10 to the minus 47. Compare this number to what we can do with the lower energy neutrinos that we had access before the IceCube discovery. These are bounds on the coupling size coming from atmospheric neutrinos, not from astrophysical neutrinos. With astrophysical high energy neutrinos, we can improve on those bounds by several orders of magnitude. And that is the fundamental reason why doing this kind of studies makes sense. Now we can extract new physics from 4 different observables in neutrinos. I'm gonna say more about this later, but this is a spectral shape, the angular distribution of the neutrinos, the flavor composition, so how many nu e, nu mu, nu tau. Remember, there's 3 types of neutrinos, but the relative contribution of each can tell us about new physics, and also the timing. And I'm gonna say more about timing as well. And we can do this in spite of the fact that measuring neutrinos of any energy is quite hard. So we have poor energy angular resolution. It's difficult to reconstruct what flavor neutrino interacted, and we don't know many things about astrophysics, the astrophysics of the sources that gave rise to these neutrinos. In fact, we don't know what the sources are. Now, I should say here, I'm not gonna say much about astrophysics. That's a completely different beast and is extremely interesting in itself. I'm gonna say more about just the particle physics part of the story. So this is the landscape. Today, we have seen TeV-PeV neutrinos. I'm going to say a bit more about this in a moment. And we're turning the predictions that existed before the discovery of these neutrinos into, finally, data-driven tests. And we're also planning for what's going to come in the next decade in the hopes that we will discover neutrinos of 100 PeV or more of energy. And that's also part of what we're doing today. So let me just tell you what the story is so far. What is the current status of high-energy neutrino physics? All right, so let me just present a toy model of how these high-energy neutrinos are made in astrophysical sources. We can think about a source like that one blazar that I showed a picture of earlier, that it has high magnetic fields that trap the protons and slowly but surely accelerate protons up to the highest energies, like 10 to the 20 or 10 to the 21 electron volts. These sources are typically also generators of some sort of photon background. So those accelerated protons can interact with the photon backgrounds. About 50% of the time, they will interact by creating a delta resonance, so a proton by the higher resonance. And then the delta resonance is very short-lived, and it decays into a proton and a neutral pion, or a neutron and a charged pion. And the protons typically have some kind of power law behavior. So it goes like e to the -2 by a mechanism called Fermi acceleration, which you might be familiar with. And the photons are typically also power laws, but now with a kink. So there's a change in the spectral index over here. And that is typical of the mechanism that gave rise to the photon spectrum. So the pi zeros, again, they decay quickly into photons, to gamma rays, and those contribute to the gamma ray emission from the source. And the charged pions decay also promptly into 2 mu neutrinos and 1 electron neutrino. I'm not distinguishing between nu mu and nu mu bar, because currently neutrino telescopes have very hard time distinguishing between neutrinos and antineutrinos. So I'm just counting 2 mu neutrinos, 1 electron neutrino. And finally, the neutrons that are sometimes created in the decay of the delta resonance are no longer magnetically confined as the protons were, but they can escape the source, and along the way, they can beta decay back into a proton, and those are protons that contribute to the ultra-high energy cosmic rays that we see at Earth. So charged particles are the highest energies. So there's the energetics of these particles are of course connected. The neutrino energy, the energy of each of these neutrinos is about 1/20th of the proton energy of the parent proton, so about 5%, and the gamma ray energy is a bit higher. But in order to understand, of course, the full story of how these high energy astrophysical sources could be making neutrinos and gamma rays and ultra high energy cosmic rays, we need to see the three of them, neutrinos, gamma rays, and cosmic rays, and that each one brings a piece of the puzzle. I'm gonna just center my story on the neutrinos. So that's about what happens inside the sources. But now, of course, the sources are distributed through a distance from a few hundreds of megaparsecs all the way to tens of gigaparsecs sometimes. Depends on the source class. So we measure things not in distance, but in redshift. And the higher the redshift, the farther away the source is. And they can be steady state if their activity of neutrino production is maintained over a long time, or transient if they're explosive and they only emit for a few months or a few seconds even. What I'm gonna say applies to both cases. Now, inside the sources, neutrino production happens by the toy model that I showed earlier. And if the the protons that interact have PeV energies, and there is a background of MEV photons, then the energetics are such that we can get out of the process TeV-PeV neutrinos. And those are what we call high energy neutrinos. And those we have seen. IceCube discovered them, and we have been measuring them for about 10 years at this point. But inside the sources, there could also be higher energy protons, EEV now, so 1,000 times higher energies, and lower energy photons. And again, by the same energetics, we now would get neutrinos of 1,000 times higher energy, and we call those ultra-high neutrinos. And not only that, but that process could also happen not by proton-photon interactions, but by proton interactions with ambient gas. And you would also get EEV neutrinos from the sources. And finally, as I said earlier, protons leave the source in the form of neutrons and other isotopes, And while they propagate to the Earth, they may interact with the cosmic microwave background and other cosmic backgrounds, and again give rise to EV neutrinos. And we call those cosmogenic neutrinos because they're born along the way. So there's three sources of neutrinos, or 3 points of production of neutrinos at the highest energies. The high energy neutrinos, we have seen. The ultra high neutrinos, we haven't, but we're looking for them. Now, experimentally, the current landscape is the following. We have 3 big neutrino telescopes. We have Antares in the Mediterranean Sea, Baikal in Lake Baikal in Russia, and IceCube, the biggest one in Antarctica. And this is the only one so far that has been able, that is big enough to have seen the flux of TeV to PeV neutrinos. So IceCube, this is the counting house that sits on the surface, but IceCube is made up of 86 strings of photomultipliers buried at depths between 1.5 kilometers and 2.5 kilometers in the Antarctic ice. And it is sensitive to the light, the chunk of light that neutrinos make when they interact in the ice with a proton or a neutron, start a particle shower, and then the charged particles inside the shower generate chunk of light, which propagates inside the ice and reaches the photomultipliers. So every time IceCube sees a flash of light in the perpetual darkness that it typically lies in, it is likely to have been a neutrino. Of course, there's backgrounds, etc., but that's the basic story. So to give a bit more detail about this, the process by which neutrinos interact at these energies is called deep inelastic neutrino-nucleon scattering. And the deep means that the neutrino is interacting with the quarks and gluons of the nucleons of the parton, or sorry, of the proton or the neutron. And inelastic means that it's breaking the nucleon apart. And that can happen in 2 ways. Either the neutrino exchanges a Z boson with the quark that it interacts with, so a neutral current event, or it shares exchanges a W boson, so it's a charged current interaction. And in both cases, the energy of the parent neutrino gets distributed into the final state products. So in the neutral current case, a neutrino comes in, breaks up the proton or the neutron into final state hadrons, which I'm calling X here, and then out comes a neutrino of the same flavor as the initial neutrino over here, and it receives some fraction of the original neutrino energy. And we call that fraction inelasticity. And the rest is going to the final state hadrons. In the charged current case, in comes a neutrino of a certain flavor, and out comes now a charged lepton, an electron, muon, or a tau, depending on the flavor of the incoming neutrino. And again, that receives a fraction of the energy. Everything in the final states that has an electric charge contributes to the chunk of light that is emitted and eventually caught by the photomultipliers that make up IceCube. And that means that IceCube sees roughly 2 types of events. It sees showers and tracks. In a shower, a new E, an electron neutrino, or a new tau, a tau neutrino, interacts in the ice by one of the 2 processes that I just showed. It creates a particle shower of about 10 meters in size or so. Particles radiate chunk of radiation, and that chunk of radiation grows outward radially from the interaction vertex for about 100 meters or so, and its light gets deposited in the photomultipliers in the strings that the light hits. And it looks fairly spherical. As you see here, it has poor angular resolution because it looks like a sphere, and you roughly can tell more or less where the neutrino interacted first, so it's at the center. But again, it's difficult to see exactly where it came from. Whereas for tracks, that happens when a new mu interacts by a charge current interaction. So somewhere in the middle of this blob, again, there is a shower around the interaction vertex that is due to the final state hadrons that are making a particle shower and again emitting chunk of radiation. But there's a final state muon that got created in the process and that left a mark as it was traveling away from the interaction vertex for a kilometer or so. And because of this, and because we know that the neutrino is aligned or was aligned with the direction of the outgoing muon, we know that the neutrino in this case came from this direction, interacted, and then out came a muon. So we have a very good angular resolution of about 1 degree or less. And very good, of course, it's very good for neutrino physics, but very poor compared to what our astronomer friends do. So from these kinds of events, mainly, we can surmise 4 different high energy neutrino observables: the energy spectrum, so the number of neutrinos per energy that we detect, the arrival directions, or where from the sky these neutrinos are coming into the detector, the flavor composition, that means the amount of nu e, nu mu, and nu tau in the incoming neutrino flux, and the arrival times. And by that I mean if we have a source, astrophysical source, that is emitting gamma rays and neutrinos at the same time, then knowing when we see the gamma rays and the neutrinos at the Earth is telling us something about the propagation of neutrinos along the way. They should arrive at the same time. If they don't, something could have happened. That something could be new physics. So we have standard expectations for all of them. We have an expectation of a power law energy spectrum for the neutrinos, roughly isotropy in the directions as an expectation. So we think that the sources are distributed isotropically around in the sky. We also expect neutrinos to arrive at the detector with distribution in directions that is compatible with an isotropic distribution of sources. We expect equal amount of nu e, nu mu, and nu tau nominally at the detector. And as I said, if a source emits gamma rays and neutrinos at the same time, we expect those to arrive at the detectors at the same time as well. Any deviation could be a sign of new physics, and I'm going to say more about this later. But before that, I'm going to give a very brief survey of what IceCube has seen in about 10 years of looking for neutrinos. I should say at this point, I'm very happy to answer questions along the way. I'd rather just get a few interesting points across that get to the very end of the presentation. So please, by all means, just interrupt me. Okay, so let me say what IceCube has seen in 7.5 years for these data set results. The first is the energy spectrum. It has seen about 100 events where the neutrino interacted inside the cylinder of photomultiplier strings that makes up IceCube with energies above a certain threshold of 60 TeV. And you see here the number of events in the y-axis as a function of the positive energy, which is a proxy for neutrino energy. You see 3 different colors. These purple histograms are atmospheric muons, so they are just coming from muons generated by cosmic ray interactions in the upper atmosphere. So those are not neutrinos, they're just background. And then we have atmospheric neutrinos made also in the cosmic ray interactions in the atmosphere. And then in order to explain the data, which are these points over here with the arrow bars, we need an extra component in yellow, and that extra component are the astrophysical neutrinos. So by now, the existence of astrophysical neutrinos of energies above this threshold has a statistical significance of like 8 or 9 sigma over the background of atmospheric muons and neutrinos. And one can fit this signal into a flux spectrum, I should say, that is single power law. So we leave the normalization of the spectrum and the spectral index of the spectrum as free parameters. We make a fit of this shape to the data that IceCube sees, and you get values for the normalization of the spectral index. And what you see here is a result of that being done with different data sets. So for this data set, that is the latest one, 7.5 years of contained events, the best fit value of the spectral index is at about 2.9. So I'm projecting the star over here. And that is pretty steep. We expected something closer to 2, 2.1. So the fact that we see 2.9 is still a bit of a mystery. And not only that, but if you use a different data set that is not made of neutrinos that interacted inside the detector, but neutrinos that interacted just outside the detector, made a final state muon, and then we see the muon crossing the detector as a signal of a original neutrino interaction, then we use those events then and make a similar fit. The best fit value of the spectral index is rather hard. Now it's like 2.2, 2.3. So closer to what we expected. The fact that we see different spectral indices as a result of using different data sets there's still a small tension there, and we're trying to understand what's going on. But simple power law seems to be a good fit so far, at least. All right. So far what we know is the following. There's neutrino energy in the x-axis and the neutrino flux or energy flux in the y-axis. And we can fit the data that IceCube sees by a power law. And I'm showing two power laws because of what I just said. One power law is due to neutrinos that interacted inside the detector, and another one is due to neutrinos that interacted outside and created a muon track which crossed the detector. And at higher energies, this reaches about a few PeV. At higher energies, we have seen nothing, but there's upper limits from the observation, I should say the non-observation of higher energy events. And that's what you see here from IceCube, and also from the Auger cosmic ray experiment, which has at these energies sensitivity to neutrinos as well. All right, so arrival directions. So far, there is no statistically significant excess in the neutrino sky map that would signal the existence of a bright point source. By that, I mean, we don't know what is the origin of the diffuse neutrino flux that I just showed. We just know that it's there. We have a few ideas about what the source number density and the typical luminosity of these sources should be in order to explain that flux, but that's about it. We trace back the direction of the neutrinos in a sky map. There is one small excess of events in this direction of the sky, but once you run the analysis and compare it to the expected background from atmospheric neutrinos and atmospheric muons, the post-trial p-value, or the probability that this was just a background fluctuation, is actually pretty big. So we cannot claim detection of a point source yet. But I'm gonna put a caveat, and I'm gonna say a few more things about that now. Because so far I've been talking about steady state sources, so sources that could last a long time, and the neutrinos from them would accumulate the longer the time we observe those sources. The story might be different for transient sources. So now timing. And again, you saw this picture earlier. This is a blazar, so an active galactic nucleus that is emitting particles along a jet, and the jet is pointed towards us. A few years ago, IceCube saw a coincident event, so a neutrino of about 300 TeV coming from the direction of a particular blazar called the TXS0506+056. And that emission or that detection of a neutrino was coincident to that blazar also being active or having a flaring state in gamma rays. So this coincident detection, which you see over here in 2017, that marked the first detection of the most likely source of a high energy neutrino that we have seen so far. So at that point, IceCube opened their archival data and looked for other potential coincidences back in time, and found that in 2015, there was an excess of neutrinos in that same direction toward that blazar, but there was no associated gamma ray flaring state from that blazar. So 2017, blazar plus gamma rays, 2014, 15, only neutrinos. Neutrinos and gamma rays, and here only neutrinos. The combined significance of detection from that particular blazar was at about 4.1 sigma pre-trial, but then a reanalysis actually decreased the significance. So this is still the most likely the first source of high energy neutrinos we have seen so far, but modeling it is proving to be particularly difficult. And there's been more claimed detections of coincident electromagnetic and neutrino emission since then, but I'm not gonna say more about this now. And finally, there's flavor. And again, the big picture for flavor is the following. We have astrophysical sources, for instance, that blazar I just showed, and we have a toy model of neutrino production. Remember, the pion decay was making 2 muon neutrinos per each electron neutrino. Those neutrinos, as you have probably heard from your courses or different talks, those oscillate along the way, and that means that they mix, and by the time they reach Earth, the relative contribution of nu e, nu mu, and nu tau, the 3 active neutrinos, is different from what it was at production time. So particularly if we make neutrinos by pion decay and we start with 2 muon neutrinos per each electron neutrino, at the Earth, after oscillations, we expect equal number of nu e, nu mu, and nu tau. And we parameterize that in terms of what we call flavor ratios. It's just the relative contribution of each flavor to the total flux. So the number of electron neutrinos to the total, the number of mu neutrinos to the total, the tau neutrinos to the total, we call that F. And we know how to calculate the expected flavor ratios at the Earth if we know what the source flavor ratios are. So if we assume we know how neutrinos are made, for instance, 2 mu neutrinos per each electron neutrino, and we know how to calculate these flavor oscillation probabilities, and we know how to do it, then we can predict what the observed flavor ratio should be at the Earth. And here's opportunity for new physics. So let me make a very quick aside because I'm going to show a few of these triangles in a moment. You might have seen these flavor triangles or alternative plots before in the literature. But let me explain what they are. Any point inside a triangle like this has coordinates that add up to 1 always. So along each axis, we show a different flavor fraction. This is nu e, this is nu mu, and this is nu tau. And each corner is corresponding to a pure flavor. So this is the pure nu e flavor, pure nu mu flavor, and pure nu tau flavor. If we put a point inside and we want to find what the fraction of each flavor is, we just need to project that point along the tick mark that we're interested in reading. So this is 20% nu e, horizontal one is 60% nu mu, and the remaining 20%, remember it has to add up to 1, is nu tau. A particularly interesting point is exactly the center of the triangle where you have equal amount of each flavor. And later on, I'm going to show not just points, but also regions inside, but the same principles apply. All right, so again, what we're going to do is the following. We're going to assume we know for a moment what are the source, how sources are making neutrinos. It could be via this pion decay process or something else. And we know how to calculate neutrino oscillations from the sources to us. And these depend on 4 mixing parameters, which are measured in oscillation experiments using reactor neutrinos, accelerator neutrinos, atmospheric neutrinos, solar neutrinos. And those are known, these mixing angles and this delta ZP, ZP violating phase are known to within different uncertainties, but are known. And from that information, we're gonna compute what the flavor ratios are at Earth. So we take again our toy model of proton photons making pi pluses and those pions decaying into muons and neutrinos, and then the muons further decay into muons and electrons, sorry, nu muons and nu e's. Then we can draw that in a ternary plot. So we start out from the full decay of the pion. We start out with 2 mu neutrinos per each electron neutrino. So that means that we can put our point here on the on this axis at 1/3, 2/3, 0. That means we have no nu tau to start with. We turn on neutrino oscillations, assuming we know perfectly well the values of those 4 mixing parameters that I just showed. And that means that it turns out that the expected flavor ratios at the Earth lie very close to the center of the triangle, where we have equal amount of nu e, of nu mu, and nu tau. If we start from somewhere else at the sources, so for instance, from having pure nu mu production, then again, we can turn on the flavor oscillations, assuming we know perfectly well the values of the mixing parameters, but we now end up somewhere else inside at the Earth, just off to the left of the center. And this can happen, for instance, if this intermediate muon over here that was producing the decay of the pion lost significant energy by synchrotron radiation if the source, inside the source, if the source has a very high magnetic field. And that means that the only high energy neutrino that we have is the one coming directly from the pion decay. These 2 muon and electron neutrinos coming from the muon decay will be too low in energy to be counted as high energy neutrinos anymore. And finally, we're going to think about another benchmark, which would be nu e bars coming from neutron decay. And in that case, we start from here and we turn on flavor oscillations and we end up off to the right of the center. Okay, and all right, so that's the story. Now, let me move on and I'm gonna show you what the big landscape of neutrino physics is that we can explore using all this information from IceCube and all our theory insight. And then I move on to show you 2 quick examples about how we do that now. Okay, so as you can imagine, the landscape of theoretical neutrino models, especially of new physics in neutrinos, at the highest energies where we had not seen anything until very recently, is pretty big, right? It's easy to wonder if we don't know what is there to stop us from wondering. And that I just have written some of our favorite or popular models here of new neutrino physics. You can see dark matter annihilation, dark matter decay, star neutrinos, long-range interactions, Lorentz and CPT invariance violation, neutrino decay, etc. We can classify them, and it's useful to do it along two axes. First, at what stage of the neutrino lifetime they act, and second, what observable they affect. So some of these will act at production inside the sources themselves. Some will act during propagation. Remember, much of the power to test fundamental physics comes from the very long baselines. And some will act at detection. And by that, I mean inside the IceCube itself, or as they propagate through the Earth and towards IceCube. And the other axis is what observable they affect. Remember, we have four of them: the energy spectrum, the arrival directions, the flavor composition, and the arrival times. And each one of these models can affect one or more of these observables. So this seemingly complex plot is actually mapping out most of the theory parameter space for neutrino physics at the highest energies. And this I see as an opportunity. The fact that it is a rich landscape, I see as an opportunity for progress. And if you're interested in this, there's a lot of interesting reviews that you can look at. And please just contact me if you want the references. Okay, this is, however, further complicated by a couple of things. The first is that currently this is what we have in terms of neutrino observations of the energy spectrum particularly. We have a couple of determinations from IceCube data, and we're turning those into, as I said, data-driven tests. We're building bigger detectors to get larger statistics. We're improving reconstruction techniques, so better measurement of the neutrino energy, etc., and trying to reduce the astrophysical uncertainties that plague these kind of studies. But the main problem here is what happens at higher energies. We want to keep going in our exploration. And the problem here is that we don't know what's up there. So this is as far as we've gone in energy, thanks to IceCube. And one can naively extend these measurements and make forecasts for what one can do if the flux continues up to infinitely high energies. In fact, at these energies, IceCube becomes less efficient at detecting neutrinos because it's too small, and the techniques that it uses, which are based on the detection of Cherenkov light, become cost prohibitive to scale if we want to build a bigger detector by putting more photomultiplier strings in the Antarctic ice. So we need to go to different technologies. And one such technology is radio detection of neutrinos inside the ice. Radio waves travel far longer before being attenuated than Cherenkov light. So you can build bigger detectors with less money and less instrumentation. And one such idea is IceCube Gen 2, which is an upcoming upgrade of IceCube, and it has a radio component that is being planned to specifically detect these ultra-high neutrinos. So not only that, we can do better than just extrapolating these observed power law fluxes, but actually build fluxes based on our best knowledge of the astrophysical ultra-high energy sources, and based on the connection between cosmic rays and neutrinos, which, remember, they should be made together. So studying cosmic rays, which we detect regularly, does tell us something about the ultra-high neutrino predictions. So we can build better predictions, and I'm going to show a few here. So all of these are based on different assumptions. Some of them are based from sources, from source modeling. Some of them are just based from our connection between ultra-high energy cosmic rays and ultra-high energy neutrinos. And you see that the landscape of models is huge. Essentially anything that spans this range is still valid. Anything below the upper limit is still valid. And the shape is still up for grabs. So we need to make predictions and in the process account for this uncertainty and see if in the best possible case in the next 10, 20 years, if we're lucky and we have a high flux, what we can do. If we're unlucky and we have a rather low flux, can we still do something? And not only that, but here I'm just showing the new plus new bar fluxes predicted at the ultra-high energy ranges. But these really are different for neutrinos and antineutrinos, and we need to account for that a bit, at least. And not only that, but each flavor is also different. So there's a rich landscape of opportunity here that needs to be mapped in order for us to understand what we can do in the next decade or so at ultra-high energies. So that's what we're doing today. So we're making predictions for a new energy regime. Of course, first we want to aim to discover these neutrinos. And by that, to do that, we need to gear our sights into new detection techniques, and we need to make better predictions of the flux, and that's all going on now. Not only that, but I said earlier, we don't even know for sure where these neutrinos are coming from. So we need to account for all the uncertainties related to astrophysics. So we don't know what the sources are. We don't know exactly what the mechanisms of neutrino production are, these energies. And there's, of course, also particle physics uncertainties, like uncertainties in the values of the mixing parameters, which earlier I took as fixed values, but really they are not. So we need to account for all of these. And the way I like to think about this is currently for the field of high energy neutrino physics, we're in a situation similar as to what cosmology was in the 1990s. So it was becoming what is now a very high precision field that is based on enormous amount of data. It's one of the most sophisticated fields, and we're getting there slowly but surely. So let me just now show you two examples. Actually, I might actually make one example because I'm running against time. And I wanted to show you something about flavor stuff for high energy cosmic neutrinos and cross-section stuff. And these two have good chances of discovery or setting strong bounds. And that's what I was picking this. In the interest of time, however, I think I will skip the flavor stuff, and I'm going to show you something about neutrino cross sections rather, which might be a bit closer to many of you. So let me talk about that. And it's how we move from measuring neutrino-nucleon cross sections, so neutrino proton and neutrino-neutron cross sections, all the way from the MEV range to the EEV range. This is a plot of neutrino-nucleon cross section divided by neutrino energy. This is a famous one for the particle data group. And all of these points that you see here are coming from accelerator experiments. And the dominant process is changing from low to high energies, going from, okay, I should say first, until very recently also we didn't have any point towards the left. And then we measured coherent neutrino nucleus scattering, and now we know what happens over there. And also, until recently, we didn't have anything at higher energies than about 350 GeV. And then IceCube came online, discovered neutrinos at even higher energies, and we were able to make those measurements. So as I was saying, it's interesting to study what's going on here as we crank up the energy. At lower energies, quasi-elastic scattering dominates. Neutrinos are turning neutrons into protons, and antineutrinos are turning protons into neutrons. If you crank up the energy more, then the neutrino is able to rattle the nucleons, excite them, and then when they de-excite, they do so by resonantly emitting a pion. And at even higher energies, there's deep inelastic scattering, and that's the process that dominates also at the energies that are relevant for us, for IceCube and whatever comes after that. And that's where, as I showed earlier, a neutrino comes in, breaks apart a nucleon, and it creates final state, either charged or neutral leptons, and a shower of final state hadrons. And of course, the fact that we have not been able to measure before IceCube neutrinos at energies above 350 GeV is because we didn't have accelerators, and we don't have accelerators man-made that are able to make neutrinos at these energies. But that doesn't stop us from making predictions of what the neutrino-nucleon cross-section should look like. And one such prediction, one of the most recent ones, is what I'm going to show you here. What you see here is neutrino energy, the x-axis, and in the y-axis, you see the average of the neutrino and antineutrino charge current cross-section. I'm just taking the average because remember, neutrino telescopes don't distinguish between neutrinos and antineutrinos. And the central value over here is the nominal prediction from what I'm calling here the BGR18 model. That's one of the most recent neutrino-nucleon predictions. And then there are two lines around it, which are the 68% errors around that. Now, there's several interesting things about how this model is built. There's a softer than linear energy dependence. So this is not just a straight line, but it's curved. And that is signaling the fact that the mass of the W boson actually matters at these energies. Otherwise, this would be a linear behavior. And there's a lot of detail that goes into the construction of this. It's a next to the order calculation of the cross section. There's nuclear corrections, heavy corrections, etc. This is the most up-to-date expectation. And we're going to compare this with has been measured so far, these energies. It is interesting to think about how IceCube measures neutrino-nucleon cross sections. In this case, for IceCube to measure neutrino cross sections, the target is the Earth and the detector is IceCube. So if we have an isotropic flux of neutrinos coming with equal intensity from any point of Earth, neutrinos that go through the Earth, so up to 1 diameter in size, might get stopped at some point before reaching IceCube. So that happens when they interact via charge current interactions. They hit a neutron or a proton, and then the neutrino disappears and becomes a charged lepton. Other interactions are neutral current, and in that case, a neutrino comes in, interacts with the neutron or a proton, but out comes a neutrino again, just with a lower energy than initially. So it gets, we get a pile up of low energy neutrinos. So these charge current interactions deplete the flux, and these neutral current interactions shift the flux to lower energies. And we need to account for both effects because that's how we're going to measure the neutrino-nucleon cross section. So what happens here is that depending on where the neutrino is coming from, the effect of the neutral current and charge current interactions will be more intense. And also depending on the energy of the neutrino will be more intense. As you can imagine, this is the neutrino attenuation. So the smallest the value of this quantity, this exponential dampening, the more intense the effect of the neutrino interactions at the Earth. So for low energy neutrinos, this dampening is very small. It's very mild. So the exponential dampening is about 1, doesn't exist. But for very high energy neutrinos of 10 eV or so, this dampening is almost fully active. So the flux is almost fully attenuated. And what you see here in the x-axis is the direction of the neutrino. So a neutrino with a zenith angle of -1 is arriving at IceCube after going through the full diameter of the Earth. And that means that the chances of it interacting inside the Earth are higher. So IceCube is sensitive to energies between 10 TeV to about 1 PeV. And for energies below 10 TeV, the Earth will be transparent. That means that it doesn't matter where the neutrino is coming from, it will arrive at IceCube without being attenuated. Whereas for neutrinos above 10 TeV, those effects that I was just talking about, the depletion and the shift into low energies, become active. And that means that whereas the neutrinos that just go through a little bit of ice before reaching the detector array are not attenuated, but the neutrinos that go through the Earth are. And comparing the downgoing neutrinos versus the upgoing neutrinos gives us a handle on the neutrino-nucleon cross section. So in other words, for low energy neutrinos, the ratio between upgoing neutrinos, which are the ones that go through the Earth, and downgoing neutrinos, which are the ones just come from above, is about 1. For high energy neutrinos, that is not 1 anymore, but it's an exponential function of the neutrino-nucleon cross section. So if we compare these numbers, we can get a handle on the neutrino-nucleon cross section. And that's what we did and what IceCube itself did, and managed to measure the neutrino-nucleon cross section for the first time at energies above 10 TeV and all the way to PeV energies. And those are different points and different curves or different data sets and methods of measuring neutrino-nucleon cross section. Okay, so far everything seems to be compatible with the standard predictions. There's no new physics showing up. Doesn't mean that there is no there. It means that there's nothing that is popping out aggressively at us yet. So far we have measured this, but we haven't measured neutrino cross sections at higher energies. And as I said, we have not detected neutrinos at those energies yet. And that's where all this richness that I was talking about earlier comes in. So at these ultra high energies, and we need to account for these different potential fluxes, the Earth is completely opaque to neutrinos. So at TeV to PeV energies, some of the neutrinos going through the Earth still make it to the detector, but at higher energies, essentially none do. So all of these will get stopped, and only the ones coming from around the horizon or downgoing ones will make it to the detector. So making that comparison between upgoing and downgoing neutrinos now gets restricted to a very narrow solid angle of neutrinos coming from around the horizon, where they can still make it barely to the detector. And that means that we have only about this region to make that same kind of measurement that I just showed you when we move to the 10 eV range. Now, of course, let me just put it in context. These, again, this is the neutrino-nucleon cross-section, and these are all the accelerator neutrino experiments that have measured it. These are known, and they might even be known a little bit better in the future with some accelerator neutrino experiments that are going to come online. This is what we're doing today with high energy cosmic neutrinos, and this is work in progress. These are the points that we have been able to measure up to PeV energies. But we want to go further, and that's where the unknown fluxes come in. And we need to make predictions for potential different fluxes that might appear. And those are different color bands that you see here, depending on whether the flux is big. We can measure we can make a good measurement of the neutrino-nucleon cross-section that is very accurate. That is the orange band. If it's a bit smaller, the flux, then the uncertainty in the measurement becomes like the green one. And if it's a rather low flux expected at the high energies, then our measurement is pretty bad. In the best possible case, we will be able to measure the neutrino-nucleon cross-section in IceCube Gen 2 in the radio array after 10 years to within the theory uncertainty. This is work being done by one of my students. Okay, so this is an example of the power of using high energy and ultra high energy neutrinos to do something that we could not do otherwise. There's no way to make neutrinos of these energies ourselves, and no way to make this kind of studies of neutrino interactions. Very well. So what I've shown you now is then the landscape of what's going on at the highest energies. Now, I didn't have time to show you some of the synergies between what's going on at the ultra high energies and the high energies and what's going on at the lower energies of oscillation experiments, but there's interesting information that comes from this regime of energies and informs studies at this regime of energies. And I hope I convinced you that there is a very rich panorama of potential models that we're trying to test. I only showed you one specific example, but there's very many things that are going on for most of these theory models that are there. Not only that, but the experimental landscape is extremely exciting. In the next decade or so, we're going to have IceCube Gen 2 hopefully built, and this means there's going to be more photomultipliers. In addition to this radio array I was mentioning, there's also going to be more photomultiplier strings getting buried in the ice, and also 3 new detectors about IceCube size. P1 in Canada, KM3 net in the Mediterranean Sea, and a new Baikal detector in Lake Baikal. And at even higher energies, so for ultra high energy neutrino detection, there's a host of different techniques that are being designed, tested, and planned for that are hopefully going to come online in the next 10 to 20 years. And we're currently making predictions for what they will be able to do and how well they will be able to do. And this is ongoing work. So we've gone through from first predictions of cosmic neutrinos when we had no discovery yet to discovering PeV neutrinos, finding the first hints of sources, doing the first new physics studies. And I've briefly shown you how we can get from here to there in 10 to 20 years, and potentially discovering EEV neutrinos and turning those tests into precision tests and measuring, for instance, for the first time, neutrino-nucleon interactions at EEV energies. So I invite you to work on this. This is an interesting, rich field, both in theory and in experiment. There's data coming, which means that the field is active and healthy. Now, I said in the beginning, in closing, that I have a special place in my personal career for Mexico, and that's actually where I spent about a year in 2006 and 2007 working with Omar when I was still a master's student. Here you see me as a younger version of myself. And then I met several of the people that are now part of your staff. at Fermilab a couple of years later. You see I'm here on the back, and we've so that's how my career started. The first international place I visited for physics was Sinvestav. So I stayed there, and I have a very fond memories of my time there. So finally, in closing, I want to invite everybody, all the PhD students, the master students, to this PhD summer school neutrinos we're organizing at the Niels Bohr Institute. It will be in July, hopefully in person, but we will probably offer remote participation too. So feel welcome and invited to please sign up. If you decide to come, there's no participation fee, and we provide some free coffee breaks and lunch and social program. It's a very rich 1-week program on neutrino theory, phenomenology, cosmology, and astrophysics and astronomy. And there's also problem sessions and discussion sessions. And for the PhD students, there's opportunity to give talks as well. So register early. You have a few weeks still. Thank you very much. And I'll be very happy to take any questions.
Thank you very much, Mauricio. And thank you. We really appreciate this very super interesting talk. Really nice. It was really nice. So I'm gonna stop the recording now. Just give me a second.